We don't want it to be too dark, otherwise. Let's see. Good morning, guys. Let us start. Okay, so lecture number 2 on surfaces. So we started last week with some, Wednesday with some standard tools, let's say, and then some examples of representations of surfaces you might have seen. So in other words, the graphs of functions, level sets of functions, and parameterized surfaces. And so now we're just going to move forward a little bit more formally with that material. So the outline for today is to finally see the, in quotes, official definition of a surface. Let's say there's, in different geometry textbooks, you'll find 2 different ways of defining surfaces. We're going to do the first one, and then there's a second one, which is somewhat more complicated. Let's say that's the definition of a 2-dimensional manifold, which we're not going to see. We'll look at the definition of a 2-dimensional embedded surface in R3. So when there's an ambient background space, Euclidean space. Then a bunch of examples, and then some calculations. I'll just go through some calculations about how to find the tangent plane, how to find the normal vector of the surface, because these are important objects which will bring us to the next stage. Okay, so this is sort of the lead-in from last week's lecture. So we saw 3 different representations of surfaces last week, and the question is, well, suppose you come across a surface in your everyday travels, and you have no mathematical representation for it, and you'd like one. You don't want to be able to describe it. So the question is, what representation do you use? If you haven't got one, if no one gives you one, it's just a surface sitting there, what do you choose? Well, now you become aware of the limitations of all 3 of the representations. So, for example, not every surface is a graph, right? The sphere has a top side and a bottom side, and you can't hope to represent it all by the graph of one function, because that function would fail the vertical alignment. So not every surface is a graph, so you can't necessarily use the graphical representation when you come across a new surface. Okay, next, level sets. Turns out that a level set is a very convenient, compact formulation or representation of a surface. So remember what a level set is, just maybe write it down. Say a function from Rn into R. So let's run a notation for this. Let's call it, well, I guess it's, so. So a level set is a system of, it's a set of solutions of an equation. So it's a set of solutions of the equation x such that f of x is equal to some constant, right? The c is some constant. So your standard example was f of x comma y comma z equals to x squared plus y squared plus z squared. And so let's call this guy here the level set of C, and level set of C is equal to, well, the set of x comma y comma z triples such that x squared plus y squared plus z squared equals to C. In other words, it's the sphere of radius square root C. And let's just make sure that this C in this particular example is strictly greater than or equal to 0, but that, of course, is not necessary for every example. But in this particular case, if you were to put a negative number here, you would have no solutions. Okay? So a level set is a set of solutions of an equation. It's very compact, right? All you need is this function f, and then suddenly you can represent a whole bunch of surfaces all at once, right? For every different value of C, you have a different possible surface. So it's a very compact way of representing a whole family of surfaces. Okay, so this is a reminder of the definition of a level set. Let's come back here. So the question was, somebody hands you a surface, or you bump into one, or something like this, and you want to describe it, what representation can you use? Can you use a level set representation? Well, there are a bunch of problems. Well, so a bunch of things. So first of all, you don't necessarily know the level set equation. How do you deduce the level set equation from nothing, or just from looking at the geometry of the surface? That's an interesting question. Second question is, let us suppose that you actually do manage to find a level set function, or maybe maybe construct one in various ways. There are some algorithms which exist to construct level set functions. But now you have to actually solve an equation to get your hands on the surface, right? So you have to study this equation, f of x, y, z equals 0, or constant, or whatever, and you have to extract a solution from it. The solution is going to be eliminating one variable, so it's representing, it's expressing, let's say, the third variable z as a function of the first two, and, well, what does it mean to solve the equation? It means if you plug that into here, you get 0. So you have to do this procedure of eliminating one of the variables, and this might be very complicated or impossible. Okay, so level set functions don't always work. Next is, what about parameterizations? How do you find the parameterization of the surface? Well, the drawback of parameterizations is you can use, in fact, this is a drawback of all these methods, but in any case, it's not visible in the case of parameterizations. Maybe you can only parameterize one part of the surface. You can't do the other side. For example, for a sphere, maybe you can only parameterize the part that you can sort of project onto the plane of vision or something like this. So you can only use parameterization in part of the surface, and so therefore, if you're dealing with that surface, you have to carry around a whole bunch of different parameterizations all the time. And furthermore, you have to know how they stitch together, right? When you parameterize this bit with one thing, parameterize the other bit with another thing, then you have to keep track of how they overlap. Okay, so there's some drawbacks. There's a drawback there as well. And finally, something common to all of these methods is none of these methods provide a unique representation of that surface. There are always many ways of representing a surface. Okay, so what do you do? Well, I guess this is a practical problem, and it's also a theoretical problem. The inventors of differential geometry had to face all four of these problems in order and overcome them in order to propose a definition, a rigorous definition of the surface. So here's the outcome of one of the, well, here's one outcome, one definition of the surface. So it turns out that this non-uniqueness problem and all the various problems about parameterizations, that's the best possible scenario. So we embrace these problems, and the definition of choice actually works with local overlapping parameterizations. Okay, so I'm going to walk through this box here. Okay, so we are going to talk about things called a regular surface. A regular surface is sort of the analog of a regular curve where the tangent vector never vanishes. You'll see why that is in a second. Okay, so what's a regular surface? So a regular surface is going to be some geometric object. So let's say it lives here in R3. Some geometric object for which a local parameterization property is true everywhere. So what this means is for every choice of point on the surface, this is the surface S right here. For every choice of point P on the surface, you can find an open neighborhood, so an open ball, let's say an open set. Turns out open sets are very important in this. We won't have to worry about why. But in any case, you can find an open set of R3, so some sort of large open set in R3. So how I'm going to draw it like this. Does this make sense? Does my perspective picture make sense here? You've got a thin two-dimensional surface, and there's a point on it, and then there's a ball enclosing that point, and the ball floats above the surface and underneath the surface. And the part that I'm going to cross-hatch here, or I'm going to hatch out here, is actually on the surface. Maybe I don't know, the perspective kind of is a bit wrong now. oh, I got it. Brilliant idea. What do you think? Is that a ball, three-dimensional ball, or ball in 3 dimensions floating above and below a slightly curved surface? What do you think? Okay, so this thing here, this blue guy, is the set V in the definition. And this crosshatched bit here is V intersect the surface. So it's the part, so it's V is a solid ball, and it, runs through the surface. So it touches the surface somewhere, and that region of intersection is called V intersection S. Okay, right. So what we're saying, or what this definition says, is that for every point P on the surface, you can find the following object: a set V and a parameterization from an open set in the plane. So there's a parameter domain down here, which is U sitting inside R2, such that you have coordinate value, like you have a parameter value here, this is U1, U2, right? And you have a mapping which sends, so here's my domain U. Okay. This guy here is my domain U. And you finally you have a mapping, use all my colors, you have a mapping from this ball into R3. So sigma maps U into R3, such that sigma of U belongs to this ball here, V intersect S, for all U inside U. So this green guy here is the parameterization, the local parameterization. Right. Okay. Right. Okay, so we have there's something missing on the. Okay, so this is the geometric picture. You have the geometric surface upstairs in R3. You have the parameter domain, which consists of 2 variables, R2, and you have a function which takes the parameter domain and maps it forward into R3 and covers a portion of the surface, maps onto a portion of the surface. That's the geometry. Okay. So that's the first box, or the first paragraph, or first sentence there. Any questions on this picture? Okay. So now the 3 different points in turn. So I seem to have deleted something from the first point. The first point, yes, it's true. I want you to be able to write sigma equals to 3 functions, sigma 1, sigma 2, sigma 3, 3 component functions. Right, so each sigma, let's say sigma 1 is a function of U. Sigma 1 is a function of U1, and U2 is that's a real number, right? So this is, so let's say K goes from 1, 2, and 3, right? So these are the component functions. Yes, it's true, I want to say that sigma has component functions, but I want to say a little bit more in this bullet point, and I forgot to put it down. What do we kind of want these functions to be? Yeah, that would be a good guess. You want them to be differentiable. So I should have put the word, you want these functions to be differentiable. And of course, you can put anything you want here. You can put any regularity condition you want here. So, in fact, generally, we're going to talk about smooth functions. C infinity is another word for smooth, and this means infinitely differentiable. So in other words, you can differentiate these things as often as you like, and you will never run into problems. Okay? So that's bullet point number one. Let's move over here. Yeah, fine. Figure it out over here. Okay, so that's bullet point number one. Bullet point number two. So I want this function to be invertible. So I wanted to give a unique description of the points in its domain of definition. So let's say this is point number one over here. This is going to be point number two over here. So let me just say that sigma is, I have to qualify this a little bit. What does actually invertible mean? You know, strictly speaking, sigma is a function from R2 into R3, 2 dimensions into 3 dimensions. So, you know, it can't be invertible as such. But what I would like to say is that the function, does that make sense? It can't be invertible because it's from R2 to R3. 2 dimensions into 3 dimensions can't be, you can't cover everything in a one-to-one. You can't be surjective in that way, right? You can't map to everything. Anyway, you can only map from 2 dimensions to 2 dimensions. So how do I make it invertible? Well, I want to say that it's a map from U, which is a 2-dimensional thing, onto V intersect S. So just onto its image. No, I'm not going to worry about trying to figure out what invertible, no, I'm not going to, it doesn't map anywhere else. I just want to say it maps into this image. So I would like to say that we have an invertible mapping from U onto V intersection S. So the picture is, you have U here, you have sigma going this way, and then over here you have your surface S, and then the blue, this blue guy is V intersect S. So you have an invertible transformation or invertible mapping from points here to points over here. And this is, so I have invertibility this way. And so whenever I'm talking about sigma inverse, in quotes, sigma inverse, what I mean is the mapping that looks only at points on the surface and gives you back their parameter values. That's what sigma inverse does. And another requirement here is that the inverse is continuous. And actually there's a theorem which says that if the inverse is continuous and the original function is C infinity with non-vanishing derivatives, then the inverse function is also C infinity, at least when you restrict it properly. But never mind about that. Let's just say continuity makes sense. We want this inverse function to be continuous. Okay? All right, so that's bullet point number 2. And bullet point number 3, so I want to control, not only do I want the function to be, to be differentiable and continuous, but I also want to have some control on the derivatives. So what I would like to do is ensure that this differential d phi is everywhere injective. So, d phi at u is injective for all u inside the parameter domain. Okay, remember what injectivity means. If the differential is injective, remember from last week's lecture, if the differential is injective, that means the differential as a linear transformation takes a pair of vectors in U and maps them forward to some transformed vectors over here. But if they're linearly independent to start with, then they're linearly independent to end, right? An injective linear transformation has this property. linear transformation with no kernel has this property. It maps a linearly independent set to a linearly independent set. Does that make sense? Everyone remember this? So I see some nodding. So everyone can nod. And I will know that I can continue. And not nod off, but nod. Okay. Right, so let me write that down here. So let's say the reasoning behind this is what you want is okay, so the reason you want to keep this guy injective is because you want d phi of u, the differential, which is a linear transformation, to take linearly independent vectors in the U space. So let me draw little guys like this, linearly independent. And they're going to, it's going to go to somewhere, right? This is d phi u acting on these vectors. So this is, let's say, v1 and v2, two vectors. Right? You still want these guys to be linearly independent as you map over. Okay? Now, linearly independent, if d phi has this behavior, what does that mean about phi? What was the gist of last week's lecture? This thing in a small little box. If d phi at a point behaves in a nice way, what do we expect for sigma? If d sigma behaves in a nice way at a point, what do we expect for sigma?
Something similar.
It's not something similar. So, and in this case, how would you describe similar? Locally invertible, okay. But in the geometric terms, maybe what you'd be doing is you'd be taking a small little square, tiny little square, like two vectors are, they're just vectors, right? They're these tiny infinitesimal quantities. But if you want to sort of spread it out a little bit, you have a tiny little square, right? That span, these edges are the two vectors. What happens to the tiny little square when you push it forward under sigma? It doesn't, the area doesn't go to zero. Sigma doesn't flatten out. It still remains some kind of diamond with non-zero area, right? Two vectors are linearly dependent if they coincide, right? So what d phi would have to do is take vectors like this and then map them forward to vectors that sit on top of each other. And that would cause the little area, the infinitesimally small area spanned by this little square that I'm pushing forward to collapse down to nothing. To sort of a pinching off effect. So you want to avoid that, of course, because you want everything to be sort of locally two-dimensional. So you impose this restriction on the d phi. Does that make sense? Okay, so I'm sort of gathering some names. So Eric and Arnek, and what was your name? I think I asked you the name. So tell me your name. Cassidy? Okay, and what's your name? Arun? Okay. All right, I remember some more names. Okay, you guys were nodding. And what's your name? Adrian. Oh, fantastic. I'll remember that. And yours?
Thomas.
Sorry? Thomas. Okay. All right. Okay, once you guys start answering questions, I'll that's what I want to hear. Okay. Okay. Sorry. Yeah. So where are we? So d phi is injective. D sigma is injective. What does this actually mean? Well, okay. So it means all this nonsense. But how do you test it? Well, how do you test if the linear transformation is injective? If it were a square transformation, you just find the determinant, right? And if the determinant is non-zero, you're good. But this guy is not going to be square. It's going to be 2 by 3, right? So how do you find that? How do you determine if a 2 by 3 matrix is injective? You do that. You find L transpose L, and then you take which is square, and then you take the determinant of that thing. That thing is if that determinant is non-zero, then you have an injective L. Okay. All right, so there you have the full and complete official definition of a surface. Well, minus what I accidentally deleted up there. Never mind. Okay, so far so good? Yeah, Michael?
Don't you want some kind of consistency condition when you have like 2 points and you have then 2 coverings and they overlap? That
you want that for the definition of manifold. If you're going to do the definition of a manifold,
that's where I remember that.
Which is in which there is no ambient space, in which there is no background R3 in which to make sense of these things, then you need to do something like that. But in this case, because there is a background R3, you can treat sigma as a set of 3 real valued functions, and then you don't need to do this overlap condition. The reason you do that overlap condition in the manifold case is because you have to make sense of what it means for a manifold to be smooth as opposed to anything else. So you need, in order to use the definition of smoothness, you need real value functions somewhere. And what ends up being a real value function is the mapping from coordinate chart, from parameter domain, to the other parameter domain, which is only defined when there's an overlap. So what you say is, whenever there's an overlap, the definition of a manifold would include the following statement. Whenever there's an overlap, then the induced real valued transformation is smooth. But you don't need to do that here because you have an ambient R3, so these things are already real valued and it's fine. Okay, any other questions? Okay, let's move to the next slide. Okay, so I'm going to erase a bunch of stuff and then we'll walk through some examples. Okay, have any questions come into anyone's mind on the previous material? Okay, so some examples. Okay, so I want to look at graphs because they're very simple surfaces and they're very familiar. And again, I don't mean graphs in the computer science sense of the word, I mean graphs in the mathematical sense of the word. So let's say, so we consider some function from, let's say, R2 into R, and the surface S, which I'm going to define as the set of x, comma y, comma z triples, where the last coordinate is f of xy. And picture of this thing is simple. You have your z-axis here, and then you have the xy plane here. And the object is, standard picture of differential geometry's picture of the surface. Okay, and a point here sits above a point xy comma 0 sitting inside the plane, and this point here is x comma y comma f of xy. Okay. And let's say an even more concrete example might be, well, we keep using the sphere, so let's go ahead and use the sphere again. Right, at least the upper half sphere, it's x comma y comma square root of 1 minus x squared minus y squared, where you allow x and y to belong to the unit disk. And so there's your upper half sphere. Okay. Right, let's put a little little caveat here. So what's not allowed? Question for you guys. What is not allowed in the world? What can I not explicitly not have in the picture? What should you not have in your minds? What's forbidden in the world of graphs? What kind of behavior, geometric behavior, is forbidden in the world of graphs? Yeah. Okay. Fine. Yeah, that's a good point. What's your name? Michael. Okay. Multiple values are bad. So in fact, two caveats. So here's some bad behavior of graphs, right? You can't have two different values above or above and below the same point. Okay, that's the first thing. In fact, I had something else in mind, but that's exactly a good bad property as well. But is there something else that we don't want to have? Yeah, what's your name? Ben. Okay, and vertical tangents are also bad. So let's say, I'm going to draw that. Here's our plane. I don't know, something like, okay, well, to figure out how to draw a vertical tangent in a smooth way. How's that? What do you think? So here, you have a place where the tangent is, here you have a place where the tangent is vertical. Okay, so that's another thing you can't have. You can't have vertical tangents. We'll come back to those. We'll come back to these two soon. We'll see that this actually arises technically. So in other words, the math tells you that this is a problem at some point soon. Okay, so these are graphs. So the question is a graph a surface? So that's the question we'll look at right now. Is a graph a surface? Well, I have to build a parameterization. So now I'm going to use, okay, so the answer is yes, and I'm going to prove that it's yes, and the proof goes as follows. You have to build a parameterization of a part, at least a part of the graph, maybe all of it, but certainly you have to be able to build a parameterization for every part of the graph. Because you want to use the definition that we just showed, right? So you need to build a parameterization. Okay, so the form of this expression here, this graphic expression, this standard form of the graph, suggests exactly how you should build this parameterization. Remember what you want. You want a function from R2, or at least a subset of R2, into R3. So you want three component functions. You've actually got three component functions right here. The first one, the second one, and the third one. Okay? So here's your parameterization. Sigma of x comma y. So in the world of graphs, x comma y is the parameter domain. Or live in the parameter domain. So the xy's that you use live in the parameter domain, and since I have made no restriction at this point on the domain of the function, it's just xy live in all of R2. Over here, the domain is restricted, right? It's just xy being inside the unit disk. But in any case, in this particular example, everything's fine. I've got all possible R2 values for xy, and the three component functions are given by x is the first one, y is the second one, and f of x comma y is the third one. So there's the parameterization. Okay? So, good, we've got a parameterization. You can parameterize a graph using parameterization, using a function of R2 and R3. What's the next thing we have to do? Say again? Okay, well, let's say we have to show that it's smooth, but let me say that depends on f. And if we choose f to be smooth, then that parameterization is going to be smooth. So let's say we've done that. Okay, next. Well, there's this invertibility question. And I guess let's not dwell too much on the invertibility question. I mean, you sort of can see geometrically why this thing is invertible, right? There's a straight line. There's one and only one straight line connecting you from xy in the R2 plane going up to the graph, right? So you have this one-to-one correspondence between points downstairs going straight up to a point upstairs. You don't have multiple values, one unique value. So there's the, let's say that takes care of the invertibility. The other thing we want to figure out is, the property of the derivatives, right? We want to make sure that d phi is an injective mapping. So let's check d phi. Okay, so how do you compute d phi? Well, d sigma, pardon me. So you want to do d sigma 1 by dx, d sigma 1 by dy, d sigma 2 by dx, d sigma 2 by dy, and d sigma 3 by dx, d sigma 3 by dy. This is your matrix. D sigma equal, and so at some point x comma y is equal to this. Okay, let's figure it out. Easy peasy, right? So sigma 1, you get a 1 up here, you get a 0 up here, you get a 0 here, you get a 1 here, and you get df by dx, and you get df by dy downstairs. Okay, so we want to compute this d sigma transpose by d sigma. That's now equal to, right, so let's make sure these are correct. 0, 0, 1, df by dx, df by dy, and multiplied by 0, 1, 0, 0, 1, df dx, df dy. Okay, does somebody want to do that real quick? Someone with pen and paper? Tell me the answer. Okay, and whoever's already found this answer, your next job is to compute the determinant of this thing. Okay? I'll give you a hint. In fact, I'll give you the answer. Okay. All right. Okay, so let's just say to save on time, let me short circuit the process a little bit. But I'm glad that you guys got started because it gives you some idea of how these calculations are done here in differential geometry. Okay, so there's your the object you have to compute. You do it, you get this matrix. The matrix doesn't tell you what you need to know just yet, but invertibility you can compute easily from it. You take the determinant. It turns out that if you find the determinant, this is what you get. You get some nice cancellation behavior. And you get this result over here. It's 1 plus the square of df dx plus the square of df dy. Okay. Question, when is it 0? Tell us. Never. Exactly right. Okay, so graphs for a smooth function are perfectly fine surfaces. That's the upshot of this calculation. Okay? Yep.
So it kind of bothered me that you made X smooth, so graphs are
Good. This is good. I'm glad it bothers you. Tell me, sorry, what's the question?
So non-smooth functions are not smooth.
No, non-smooth functions are just less smooth surfaces. There's a if you define surfaces, so no, they're not smooth surfaces, but they're reasonable geometric objects anyway.
Right.
They're just less smooth surfaces. So you might have things with, with
Yeah.
linear kind of stuff, or it's a lot. Yeah,
Okay.
definitely right. Yeah.
So in our definition, like with a cone, is that okay?
Well, yeah, a cone is a perfectly reasonable, obviously, is a perfectly reasonable mathematical object.
Yes.
And you can express it by means of a graph of the square root of x squared plus y squared. Z equals square root of x squared plus y squared, I guess. I think. Because if you set x equals to t and y equals to t, so you're moving out in a straight line, then you get z equals to t, so you're moving up also. Yeah, so fine. You get a cone. Absolute value of t, you get a cone. Yeah, works perfectly fine. It's just you wouldn't call that a smooth surface. You call that a surface with a I don't know, C1, a failure of a conical singularity at the origin. You just have extra structure. You just have to spend more time describing what's going on at the singular point, but it's allowed. Yeah. You just have to be careful when things happen. Well, you just have to be careful around the singularity. And sometimes around the singularity, these calculations give you misleading answers. I'll try to think of it. Send me an email and I'll try to think of an example where things go different than you expect. Okay. Right. So there's our proof that a graph is a regular surface. Okay. Let's just do this. Does that make sense, everyone? Did you have a question for me?
I was going to ask, the determinant you check is equivalent to checking the two column vectors are linearly independent.
Yeah, that's true. I mean, you sort of eyeball this. Yeah, it's infinitely independent. It's true. Okay. It's just that actually this quantity, this 1 plus dx squared plus dx dy squared, that quantity shows up all the time in differential geometry, so it's good to see it the very first time where it originates. Okay, so let's look at bullet point number 2. So now that we know that graphs are surfaces, now we can prove that a sphere is a surface. A sphere itself isn't a graph, but you could represent it as the union of 6 different graphs. What are those 6? Well, you can do it in several different ways, actually. But let's say, how do you come up with 6 different things, 6 different graphs to prove that a sphere is a surface? Cover a sphere. Okay, could you raise your hands and do that again?
Well, x squared plus y squared plus z squared equal to 1.
Yep.
So we can start with z equal to square root of 1 minus x squared minus y squared. 1 minus x squared minus y squared plus minus, so that gives a hemisphere on the top and the bottom. But we haven't represented the equator. It's equal to 0 yet.
Okay.
So similarly we do it with x and with y.
Yep.
It's totally get every point on this.
Yep. Yeah, exactly right. Okay, so just to say that again, I'm going to add one point. So you have 6 different graphs. You can use the equation x squared plus y squared plus z squared equals to 1 to get 6 different graphs. You can isolate the z, the x, or the y, and you can choose plus or minus 1 in that square root. That gives you the top hemisphere, the bottom hemisphere, the back, the front, the left, the right. Okay. In each case, each one of those graphs is insufficient for 2 reasons. First, it clearly doesn't cover everything because the top doesn't touch the bottom, right? So you need the other side. But you're also not touching the equator. Right? I need to be open. I need to talk about the open hemisphere covering the top. I can't use the equator. Why not? problem with the equator? I'll let someone else answer. Why not? Yeah, you have vertical tangents there, right? The vertical tangents happen at the equator, so there's going to be a problem represented that graphically. Mathematically, how does the problem manifest itself? Yeah, non-smoothness. Think of the function. The function is the square root of 1 minus x squared minus y squared. The derivative, when you differentiate the square root, where does the square root go? It goes in the denominator, right? And so now you have this derivative, so let me write it down, sorry. So you have f of x comma y equals to 1 minus x squared minus y squared square root. You get df by dx. This is equal to minus x over square root of 1 minus x squared minus y squared. This is a perfectly reasonable function, provided the denominator doesn't vanish. But at the edge of that coordinate chart on the equator is precisely where this thing vanishes. Okay, so problem, we can't use it here. Maybe this actually might be an example of where things work a little bit poorly. Because the surface actually is completely regular and fine at this. The sphere perfectly regular on the side. It's just the parameterization, or the coordinates you've chosen. This representation you've chosen fails to tell you anything. You could be mistaken into believing that the surface doesn't exist there, or the surface has really bad properties there. But it isn't the fault of the surface. In this case, it's just the fault of the coordinate chart.
So you just end up covering everything.
Yeah. Yeah. Right. Okay, so that's why you need 6. You need 2 for the top and the bottom, and then because you haven't covered the equator yet, you got to do it this way, but now you're missing the 2 points, the front point and the back point. You got to cover them as well. Then every point is covered. Okay? Okay. Right. So how are we doing for time? Now is where I get, so as soon as the word more sophisticated example comes in, I tend to waste 20 minutes of last time. But let's, let me erase and I'll think this through a little bit. Does these 2 examples make sense to everyone? Okay, so who's up for a challenge? Okay, I think I'm going to skip inverse images of regular values for now. I'll do the important stuff. I'll do the stuff that I really want to get done today. And then I'll come back to this. I think there's going to be enough time. I'll come back to it. So let me just go through, see there's a theorem and a proof. And it's kind of, I mean, it looks great. We've got to do this. But let's move to here. Okay, so this is sort of key material, so I want to make sure I get through these next 3 slides. Okay, so now that we have surfaces and we have representations of surfaces and the definition of surface, we've got to start getting at so now we have the geometry. But we don't really have the differential geometry yet. What I mean here is I need tangent planes. I need things that are like first derivatives of surface. I need tangent planes. So let's define the tangent space of a surface for the next little bit. Okay, so we're going to start with the very first bullet because, again, curves is a good place to start. So one-dimensional example is a good place to start. Plus, it's important. Okay, so how does it work? So let's say we've got, just draw the standard picture. Here's the surface. This is S. There's a parameterization. There's the parameter domain over here. This is U sitting inside R2. Okay. There's your standard picture. And I don't know, let's say the origin goes to here. So this is U equals to 0, and this is sigma of U. All right? Okay. So curves, how do I get curves on a surface? So a curve on a surface, or in a surface, is a curve in the standard sense of the word, so R3, curve in R3, standard sense of the word, except it never leaves the surface. So it's always a member, it's always part of the surface. Okay? So something like this, right? Well, it doesn't look so good. Hang on. We're going to make it go like kind of like this. So this is going to be our curve, let's say gamma. So and gamma, of course, is a function from, I don't know, -1 to 1 into R3. It's a standard curve, except I want to say gamma is contained inside S, or in other words, by saying exactly the same thing, gamma of t belongs to S for every t. So it's a three-dimensional curve, yes, except it's living inside that thin surface, which is S. Okay, how do you represent curves in a surface? Well, one way of doing it is by pulling them back, or by assuming that they come from a curve in the parameter domain. So a way to get a curve in a surface is you have, I don't know, you have something like this. You have gamma 0, which goes from, let's say, -1 to 1 into U, and so the key thing is that gamma of t is equal to sigma acting on gamma 0 of t. This is the key thing. So the key thing is that curves in a surface are always of this form, where you have a curve in the parameter domain and you push it forward into the surface. So here's an example, just using the sphere again. Remember, the sphere is parameterized by, this is sigma of x comma y equals to x comma y comma square root 1 minus x squared minus y squared. And so there's my parameterization, and let me take my gamma 0 to be a straight line in the parameter domain. So tt, straight line in the parameter domain. And I can push that curve forward so it lives in the sphere, and that's t comma square root of 1 minus t squared. Minus another t squared, so 1 minus 2t squared. So the picture here is this, and then here's the sphere, right? The upper half sphere anyway. Yeah, so let's say in red down here is the curve t comma t in the parameter plane, and in green, in red, curved is sigma of t comma t. All right. So this is how you put curves on a surface. Okay. What are the coordinate curves? So the coordinate curves are standard curves. This is the canonical curves relative to a coordinate chart. Well, one of these parameter domains, I should say. So a coordinate curve is the same construction on the other side, except what you do is you use these curves. these are, so this is U1, this is U2, so these curves are U1 equals to T, and U2 is equal to constant. And then, of course, and the other set of curves, the other set of coordinate curves are these guys. These guys here are U2 is equal to T, and U1 is equal to a constant. And this network of curves maps over to some network of curves on the surface. So these are the coordinate curves. It's the images of the coordinate lines from the parameter plane into the surface. Okay? So I can draw, does it make sense? So I can draw a really nice picture here. I can draw a picture of the injectivity of sigma. It's kind of a nice thing to add to this picture. I can visually represent the injectivity of sigma in this picture. Not the injectivity of sigma, I should say, the injectivity of d sigma, of the differential. How do I do that? How do I show the injectivity of d sigma in this picture right here? Let me give another hint.
All the little squares.
Little squares, yes, exactly right. Yeah, very good. Okay, so little squares, or another way of saying little squares is little vectors. So here's a little vector. Here's a little vector. And here's a little square. So Koski was a little bit hallucinogenic, but never mind. That goes, let's say it goes over here. Goes over here, let's say. And I'm just making this up here, but, and one little square, right? So let's say this, squares don't collapse. Equivalent to vectors don't go parallel. Equivalent to injectivity of d phi. Or d sigma. I should have made it phi. So, injectivity of d sigma. Okay, perfect. Those are the coordinate curves. Okay, we're getting very close, especially with this picture here, we're getting very close to being able to define tangent vectors on a surface. So here's what you do. Remember that tangent vectors, we talked about this at the beginning of last week, or I don't know when we did. We talked about this recently. Tangent vectors are represented as, like vectors, I should say vectors in space, just vectors just sitting there, are represented by derivatives of curves that you make pass through that vector. Okay? So in fact, I use curves to define vectors. I can do that in the surface context also. So here's my parameter plane, here's my parameterization, and here's my surface. And let me say I've got a curve here. This is a sigma 0, gamma 0. And then we have a tangent vector here. This is gamma 0 dot. Let me push the whole picture over to the surface under the parameterization. So I've got this. This is sigma composed gamma 0. And let's say this point maps to there, and I get a vector here. And let's call this vector v for now. Okay, v. We have a formula for it from last week, some previous lecture. So we have a formula for v. What is it? In fact, Wednesday. What's the formula for v? Socratic method. Who's smiling most proudly? Okay. What's the formula for v? Yeah, exactly right. It's d phi, the derivative. Let's give this point a name. I don't know, let's call this point u. Right? So d sigma at u multiplied by gamma dot 0. So it's the push forward of gamma dot. Okay, and the key thing, this thing is tangent to the surface. So there's how we get tangent vectors on the surface. We take curves in the parameter domain, we push them forward, and we differentiate them. Alternatively, well, equivalently, because we worked out the chain rule formula last week, you take the tangent vector of the curve and you push the tangent vector forward using the differential. Okay? Okay. Make sense? Okay, so let's look at the box. We've got everything we need to understand the official definition. So suppose we have a parameterization, and we're going to define the tangent plane of the surface as the image under d phi of all possible tangent vectors. Right, so the image of the linear transformation is the push forward of all possible vectors. Right? So maybe I can draw a picture of that too. The picture is, you have here the parameter plane, you have your parameterization, you have the picture I've drawn 1,000 times, and then you have a point u here, and then you have the tangent plane here. This is TP of u, T little u of big U, even better, T little u of R2, right? It's just the tangent. It's all possible vectors sitting at u. And this thing gets mapped forward under d sigma at u, and you get this picture. So over here you get sigma of u, and then at sigma of u you get a tangent plane. And this, they put that point in the middle. You get a tangent plane. This tangent plane is, spanned by these coordinate vectors, let's say, right? So this spanned by d sigma of u acting on coordinate vectors, 1, 0, and 0, 1. Okay. And this plane here is d sigma of u acting on the tangent at u2. So in other words, it's the image under d sigma of u. All right? And this thing is called T sigma of u of the surface. So let me write that again. This word that I just scribbled on the board is denoted T sigma of u of the surface. Okay, so there's our official definition and the accompanying picture. Okay, so now if you're, so we've been harping on parameter independence for many times in the past couple lectures, and you've got to realize that I just used a parameterization to define something. And a priori that's bad, because parameterizations means it's not unique, and you change parameterization to get something different. But this really is something that you have to do. In fact, there's a general principle of different geometry work here, and that is you just have to define some geometric concept using a parameterization. There's no way around it. But then, in order to sort of establish it rigorously, you have to show that whatever you define is independent of that parameterization. And that brings us to the parameter independence of the tangent space. So maybe I won't explain this too carefully. Let me just, because I did promise that we would only do sort of a rigorous parameter independence computation once. We've already done it once. We've done it for the arc length integral, so I don't need to do it so carefully. But the way it sort of goes is if you have two different parameterizations, sigma and tau, for the same region of the surface, then what you have is you have a mapping from parameter domain to other parameter domain, which goes through the surface. Right? You can go from this parameter domain to the surface. You can go from this parameter domain to the surface. They're both invertible mappings, so you can go like this or like this. Right? So you have this object, which goes between the parameter domains down below. So what you can write down very formally, but nevertheless it's rigorous, you can say the image of d sigma is equal to the image of d sigma where you stick in tau and tau inverse. So this is just the identity. So I'm not doing anything here. And now I break this up into two pieces. There's a theorem for this. The differential of the composition of functions equals the product of the differentials. What's the name of that famous theorem? The chain rule, right? The most famous theorem in calculus. Okay, the last line, I want to link the image of d sigma, so here it's equal to this linear transformation times the differential we're interested in. So if I multiply the column space of a matrix by an invertible transformation, does the column space change? Nope, it does not. It's just a linear transformation, invertible linear transformation of the columns itself, which preserves the column space. So that's how I can go from here to here. Right? The image of a transformation is equal to the span of the columns. So I'm going from here to here. And I have parameter independence. So we don't have to worry about learning this proof by heart. It's just realize that I've defined something by a parameterization, and in the background I've always got to have a proof like this, where you show that things are independent of parameterization. So I'll post this online and okay. Right, so let's finish off on finding a basis for the tangent space. The tangent space itself is a geometric object. As this proof shows, the tangent space is a geometric thing which is independent of parameterization, which is completely, rigorously, geometrically defined. But a basis for a tangent space isn't exactly well defined. I mean, it's well defined given the parameterization, but because you can choose different parameterizations, you get different bases for the tangent space. So whenever you choose a basis of the tangent space, you're always making sort of an arbitrary choice. You always have to keep that in mind. Okay, so let me just tell you what your options are. So let's say two ways. How do I get a basis? Okay, so what you do is, suppose we have a parameterization from U going into R3 that gives the surface. Okay, so standard picture. All right. And what you do is you say V1 is equal to d sigma at U acting on 1, 0, and V2 equals d sigma U acting on 0, 1. So if we're over at U here, that's really just taking this vector. This is 0, 1. And this vector here is 1, 0. And really, it's just pushing them forward to the surface. V1 and V2. So that's how you get a basis of densities. You take your parameterization and you apply the the differential to the coordinate vectors. And I should say, this guy here is d sigma by du1. Right? Just imagine you're taking the first column of the differential matrix. The first column of this is this. And then, of course, this is the second column. Okay, so for example, a graph. Let me finish on this example here. So for example, a graph, our sigma of x comma y is equal to x comma y comma, well, square root, but let's just say, keep it generic, f of x comma y. So in this case, my v1 is I take the derivatives in x of this function, right? So I get 1, 0 df by dx, and I get v2 equals 0, 1 df by dy. There's my example. So just do this construction there, and I guess that covers my second arrow there, my second example. And since we didn't do level sets, we didn't get to my challenge after all. I knew that was going to happen, I guess. Since we didn't do level sets, I won't do point number 3. I'll wrap that into my next lecture, which is going to be next Wednesday. So next Wednesday we start with curvature. And so in fact, we're going to start with level sets and normal vectors, and we do here, and then we're going to go into curvature. Okay, so any questions on this stuff? Okay, that's it. Thank you very much. Have a good day, and we'll see you guys on Wednesday.